Hi everyone, and welcome back to another session about using WEKA in the assessment of power system assets. So today I'm planning to have different data set, different problem to analyze. So basically, as I mentioned before we go through the data, let's try to understand this data set so that we really understand the problem or the classification problem. And I always said that before you start doing any classification or regression, you have to understand your problem. You have to understand the physics behind what is going on. Otherwise, machine learning could be really misleading. So today we'll talk about a classification problem, and we'll try to classify different types of external discharges. And I will do that in two steps. I will start in this session talking about distinguishing between external discharges coming from controlled samples, and I'll explain that. But why we are doing this? Outdoor insulation systems like termination, insulators, bushings, they are subjected to two main issues. The first one is pollution. And this pollution with the wetting on them, this will lead to dry band arcing. So an arc on a wet surface. Also, those insulation systems as well, they are subject to aging that will lead to crack, especially in ceramic insulators, or more specifically to porcelain insulators. Because of the variation in the temperature between the summer and the winter, then there a crack with time will start to develop, and this crack on the surface of the insulator will lead to external discharges. But you can see here the difference between these two discharges. This is somehow wet and this is dry, but both are external discharges. Also, you have to also understand that since this is an external insulation system, we have also corona there. That can also be measured by any measuring device that we will be using. So you have also to keep this in mind, that you have a wet surface discharge, you will have a dry surface discharge, but also there is another or a third category of discharge coming from corona, not surface, but it can interfere between these two classes. So what we're gonna do here, we will use the ultrasonic sensor, and I will be using this specific sensor to do the measurement of the external discharge. So let's try to understand a little bit the setup that we used. So this work has been done under lab conditions. Okay. So this is the setup. We have three different types of discharges, and this is what we call the test object. So you can call this as like a class one sharp electrode. So this is basically represent corona. Then we will have a smooth electrode touching a dielectric material. So you can say that this is representing a dry surface discharge, or a discharge coming from a crack on the surface of the insulator. And then finally, we have exactly the same like this setup, but now we have wetting on the surface. So this is like a wet surface discharge, or it could represent dry band arcing when there's a pollution, wetting, and then we'll have arcing. So basically, we have these test samples here. We apply a high voltage coming from a high voltage transformer that can supply up to 150 kilovolt. And then this is the acoustic sensor. We fixed the distance around 1.6 meter from the sample, and we will start apply the voltage, capture signals, and collect the data. The sensor acts in the following manner. So basically, this is the original acoustic signal. Okay. Then internally in the sensor, there is a high pass filter, so it will filter the low frequency component and keep only the high frequency component. And then it will take the envelope of that signal. So you see, this is the envelope of this one, and it will demodulate it over the carrier frequency of this country. So here our frequency is 60 hertz. In some countries is 50 hertz. And then you will get here the f of t, and this is a typical f of t in North America. So this is, you see here, 60 hertz, 120, and 180. So let's see a typical signal from Corona. So this is the time domain. This is the envelope detection. And here is the f of t after doing the demodulating the signal over the 60 hertz. So we'll see here, basically, we have 60 hertz. We have here 120 hertz, and here we have 180. These are the most dominant components in our signal. So basically, our feature vector is basically composed of 3 components: the 60 hertz, the 120 hertz, and the 180 hertz. So this is my input feature vector to classify 3 different classes: corona, wet, and dry surface discharges. So that's a brief description of the data. Let's now go and try to see the data itself. Okay, so I will just go from here, and let me open the data itself, and just have a look. As I said, it's always important to have a look to the data. So this is my data. Okay, it is in CSV file, and we want to see how it look like, the data. And I mentioned before, if anyone want to have this data, then you just please contact me, write in the comment, and I will be glad to send you the data. Okay, so this is the 60, 120, 180, and the discharge time. So we have here 60 hertz, 120, 180, and then we'll have here how many samples of this. If you go scroll down, we'll have 100 signal of corona. Then this is the dry surface discharge, and we have another 100 of dry surface discharge. And then we have the wet surface discharge. This is the third class, and we have only 50. Okay, so this is very interesting. The data is imbalanced. We want to see if we are getting the same bias we had in the transformer data or not. Okay, so this is our data. Now let's go to WEKA. Let's open the data. Okay, so we'll open the file from here, YouTube. This is the file here. So let me CSV file, and this is my file, type of discharges, open. Okay, so this is my data. This is the 60, 120, 180 hertz, and this is the discharge type. As you can see here, for corona we have 100, for dry we have 100, for wet we have 50. Okay, so we will do the 4 classifiers we learned: the ANN, we'll do the SVM, the KNN, and the G48, and compare between them. So we'll classify, choose. I will go for functions, and then we'll take the multi-layer perceptron, which is the ANN. I will come here. I will make this one hidden layer. Okay, ready, start. Go ahead. Okay, let's look here. So the accuracy, as you can see, is 95.6%, which is really good. Now, when you look here, we have 100, 100, perfect for the corona and for the dry. So there is no single misclassified, but the wet surface here, we have only 39 and 11 misclassified. So the true positive for this is 78%. So it's sort of like the bias that we are talking about. Okay, let's just try to increase this to 2, from 1 to 2 hidden layers, and let's see, are we getting the same consistent results? Start. Oh, 98%. That is way better. Now, here in Corona, there is 2 misclassified, in dry surface discharge 1, and only 2 in the wet surface discharge. So you can see here that there is no bias. And even looking here is 98% for the Corona, the true positive, 99% for the dry, and 96% for the wet. So it's very, very comparable. Is that only for this classifier? Let's try some other classifiers. Okay, let's go to the SVM, and let's start SVM. It's 98%. Okay, this is 98. Only 2 cases misclassified for the Corona. For the dry, all classified. And this is only 3 cases. We have 94%. Okay, so it's not bad. Let's choose another classifier, which is the KNN now. Okay, we'll go to KNN, start. This is KNN1, get 98%. Again, only 2 cases misclassified. Let me play a little bit with the KNN. Let's have it as 3. Let's see what will happen. Okay, start. Oh, wow, it's 98.8%, and only 1 case misclassified from the wet surface and 2 from the Corona, total of 3. Okay, the KNN seems working better than the other classifier. Let's make it 5 and see what will happen. Start. Oh, 99.2%. Wow, that's really wow. The wet surface has 0 case misclassified. The Corona we have only 2 cases misclassified from everything. Okay, that's really good. But this is, I mean, what I want to hint here so far, that this is against what we learned from the previous transformer data. When we have imbalance in the data, the classifier was biased towards the the cases or the classes that has high number. Okay, and the marginal, if you remember, in the transformer oil, the marginal oil case, it was completely like 50%. That is the best we can get accuracy, that in the true positive. This way, here we are getting 100%. The last classifier I'd like to do is the tree. I will do the J48, start, 97.6%. Maybe this is in completely relative perspective, this is the worst, but it's not really, it's not that bad. The question is why we have this problem. Why we not a problem actually, why we have this good results. Not, this is not a problem actually. So let's go to the data and let's visualize it. And let's look here. I mean, this is how you visualize the data. Here you can have the y-axis and the x-axis. For example, if you want to see 120 versus 60, and let's look here. So these are the 3 classes that we have. The blue is the Corona, the red is the dry surface, and the wet is the green. Okay. Now you see here that these classes are completely separable from each other. Very easily you can distinguish between them. So even the the wet surface is less, is half, but it is, as you can see here, it is by itself. It does not really uh, interact, or it overlap with the other classes. So this is why the classifier could recognize it, and we get a very high accuracy from this case. So looking to the data is very, very important. How about the IFT problem? Do we have the same thing or not? Okay, so let's go back to the presentation here. So let's see the data there. So this is what I just showed to you. Here is the classification accuracy. As you can see here, KNN5 get me the best results. Okay, but as I mentioned, the difference is not that big, between 99 to 97%, 2%. That is what expect to get. Now, let's look to this figure. This is what I just showed to you, that we have the 3 classes, will distinguish between. But here, when you look to the 3 classes, the bad, the marginal, and the good from the previous example, You see here the red, the marginal, they are getting inside the class. It overlap a lot with the classes. And this is why the classifier will look to the green and to the blue will be biased towards those classes, and it will be misclassifying this because first it has a lot of overlap, and second, the classifier will be looking more or biased more towards the high number classes. So in this example, we learned something very, very important, that it's not always the imbalance in the data, not always bad if we have classes that are somehow not overlapping with each other and somehow linearly or non-linearly separable, then the classifier can work very well on these classes. Now, what's next? What I'm gonna do next in the next tutorial, I will bring data from real insulators, and we'll see the difference. Now we are getting extremely high accuracy here for the controlled discharges, but as we know it, this type of discharge will not be in the field. This is the starting point because we start with a controlled samples, and we are expecting to have a very high accuracy, because if we could not get high accuracy at a controlled sample, if you go to the real samples, then definitely you will get even much worse. So this is very encouraging. Next time we'll bring real ceramic insulators, and we'll try to see how much accuracy we can get from these defects: surface crack, wet surface, and from corona. Thank you for joining me, and see you soon.